Hello everyone, I am going to do the best I can to explain the practice problems for integration solutions that I have posted for you online. So as you can see here, I have the Word document that has all those practice problems pulled up for you, and I will just go back and forth between the Word document and the PDF of me solving those problems. So the first one is asking you to find the first three terms and the last two terms. So notice this sum is going from 1 to 50. So for the first three terms, I'm going to plug in 1, 2, and 3 for I, and then plus ... For the last two terms, I'll plug in 49 and 50. So when I do that, when I plug in 1, I get 2. When I plug in 2, I get 24. When I plug in 3, I get 90. Add ... Add. When I plug in 49, and when I plug in 50. So there's the first three terms, plugging in 1, 2, and 3 for I. Here are the last two terms, plugging in 49 and 50 for I. For the next one, we're actually evaluating the sum. So I want to plug in 1, plug in 2, plug in 3, plug in 4, plug in 5, and plug in 6 for I. So when I do that, when I plug in 1, I'll do 2 raised to the 1 minus 1 plus 5. Then I'll plug in 2, 3, 4, 5, 6. And I end up getting 6 plus 7 plus 9 plus 13 plus 21 plus 37, which will add together to get 93. Now for this one here, we're going to write the sum of 3 plus 7 plus 11 plus 15 plus keep on going plus 63 using sigma notation. So we need to find what the pattern is. There is actually more than one correct answer. The one I came up with was the sum from 1 to 16 of 4i minus 1. So plug in 1, 4 times 1 is 4, minus 1 gives me 3. Plug in 2, 4 times 2 is 8, minus 1 gives me 7. Plug in 3, 4 times 3 is 12, minus 1 gives me 11. Keep on going, plug in 16, 4 times 16 is 64, minus 1 gives me 63. However, another way that you could do this is you could take the sum from 0 to 15 of 4 times I plus 3. So 4 times 0 plus 3 would be 3. 4 times 1 plus 3 would be 7. 4 times 15, which is 60, plus 3 would give you 63. So instead, we could have the sum from I equals 0 to 15 of 4i plus 3. Estimate the area under the curve. Okay, so let's take a look at this. I want to know what the area is under 2x squared plus 3, starting at 0, ending at 5. But I'm going to use 5 rectangles, and I'm going to use the left endpoints, and then I'm going to do the same thing with the right endpoints. All right, so the first thing we need is our delta x, our partition, which is b minus a over n. b is our endpoint, our larger endpoint, minus a is our smaller endpoint, over n is the number of rectangles we're going to have, which gives us a partition of 1. So now each xi is going to be a, our starting endpoint, plus however many I delta x's you have, right? Keep adding a partition. So a plus I delta x is going to be 0 plus I times 1, or just I. So now you have a couple of choices here. One thing you can do is figure out what all the endpoints are. You know you're starting at 0, you know you're ending at 5, and you know your partition is 1. So that means your first interval would be 0 to 1. Your second interval would be 1 to 2, then 2 to 3, 3 to 4, and 4 to 5. So if you write out those intervals, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, then you have all your left endpoints and all your right endpoints, and you're welcome to do it that way. But if you want to do it the formal way, and I put that in quotations, formal way, then we can start with our left endpoints. Xi star would be xi minus 1, which since we said xi star was I, then I minus 1 would be I minus 1. So then we would take the sum from I equals 1 to 5 of xi star times delta x, which would be the sum from 1 to 5 of f evaluated at I minus 1 times our delta x, which notice here we found to be 1. So f, which is 2 times your input squared plus 3, would be 2 times your input I minus 1 squared plus 3. So then we can plug in 1 plug in 2, plug in 3, plug in 4, plug in 5, and we get 3 plus 5 plus 11 plus 21 plus 35, which is 75. Now for the right endpoints, your xi star is going to be I. So we'll do the same thing, except instead our f of xi star will be f at I, which will be 2i squared times 1. Our delta x is still 1, so then we can plug in 1 to 5, and that'll give us 5 plus 11 plus 21 plus 35 plus 53, which gives us 125. So we're estimating that the area under the curve of 2x squared plus 3 from 0 to 5 is obviously going to be somewhere between 75 and 125, right? Our left endpoints gives us an underestimate, and our right endpoints give us an overestimate. So we know that the area between the actual area under the curve will be between those two values. Here we want to estimate the area under the curve with 5 subintervals. We want to use the right endpoints, the left endpoints, and the midpoints. So we're breaking this up from 0 here to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see we're 0 to 10. We're breaking this up into 5 subintervals. So we have the subinterval from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. So we'll use so when you do this, you can write out those intervals, right? You can write out 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. And then when you use the left endpoints, you'll use 0, 2, 4, 6, and 8. When you use the right endpoints, you'll do 2, 4, 6, 8, and 10. And when you do the midpoints, you'll use 1, 3, 5, 7, and 9. So that's what I did here. I drew it out for you. The right endpoints, right? We're going to draw all of them, 2, 4, 6, 8, and 10. And then you just use that function evaluation, right? The width of the interval is 2, so 2 times the function evaluation, 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 2 times the function evaluation. And we get 6. Drew it out for left endpoints. We're going to use 0, 2, 4, 6, and 8. Same thing here, as you can see. And then for the midpoints, we're going to use 1, 3, 5, 7, and 9. Same thing. Width times height plus width times height plus width times height plus width times height plus width times height, where the height is your function evaluation. For number 6 here, we're going to express the limit as a definite integral. So we're not actually going to solve it this time. We're actually just going to express it as a definite integral. So we have to look at this. So here we're going from 3 to 5. That tells us our a and b. So our definite integral is going to go from 3 to 15. Our xi star is our function, helps us with our function evaluation, and our delta x is whatever our partition is. So here we can see we're going to go from 3 to 5. Our function is going to be, here we would replace xi star with whatever our function evaluation would be, of course, x, so 4 minus x over 5x plus 3, and then we are integrating with respect to x. For number 7, as we do this, as we express a definite integral as a Riemann sum, I'm not doing a partition here. I'm not doing a, finite number of rectangles here. So we're going to have to set this as a limit as n is approaching infinity. We want the number of rectangles to go off to infinity. So this would be the limit as n approaches infinity of the sum from the limit as n approaches infinity, the sum from I equals 1 to n. It's going to be the width, f of xi star, times the height, delta x. So we have to figure out our partition, delta x, which is b minus a over n, which you can see is going to be 4 minus 1, right? That's my a and b, so 4 minus 1 over n. N is technically infinity, so we'll leave it as n, and we get 3 over n. Our xi star is going to be a plus I delta n. So a is where I start, which is 1, plus I times our delta x, which is 3 over n, which gives us 1 plus 3i over n. Now, typically, like we said, to make these Riemann sums a little bit easier, we want to use the right endpoint. So if we're going to use the right endpoint, then our xi star is just going to be xi. Well, our xi we just found right here is 1 plus 3i over n. So my function evaluated at xi star, which is xi, it's going to be my function evaluated at 1 plus 3i over n, which is 1 plus 3i over n cubed minus 4 times 1 plus 3i over n. So then when I put it all together, I've got my limit as n approaches infinity from I equals 1 to n. Here's my f of xi star times my delta x, and there I've set up my Riemann sum. Now again, I didn't ask you to solve it, I asked you to just set it up. Now in the next one here for number 8, I do actually ask you to solve it. So we are going to evaluate the definite integral from 0 to 2 of 2x plus 1 dx using Riemann sums. So we're going to go through the same process. Find our partition, b minus a over n, which we have our b is 2, our a is 0, over n is just going to stay as n. So we get 2 minus 0 over n, or 2 over n. Our xi is going to be a plus I delta x. A, my starting point is 0, plus I times, I just found delta x to be 2 over n, so I get 2i over n. Again, choosing the right endpoint typically is a little bit easier, so I'm going to let xi star be xi. So then my height will be f of xi star, which will be f evaluated at 2i over n, which if you look at f, it's 2 times your input plus 1, so 2 times 2i over n plus 1, which gives me 4i over n plus 1. So now, right here, I've set it up as my Riemann sum. The integral from 0 to 2 of 2x plus 1 dx is the limit as n approaches infinity of I equals 1 to n. Here's my f of xi star, 4i over n plus 1, times my delta x, 2 over n. All right, so now I have to do all this math. I'm going to go ahead and distribute that to n, which gives me 8i over n squared plus 2 over n. I can separate these Riemann sums using my laws. That sum of two terms being added is the sum of the first plus the sum of the second. Now, the 8 and the n squared have nothing to do with I, so I can pull them out. The same thing here, this n and the 2 have nothing to do with I, so we can pull them out. So this is going to be the limit as n approaches infinity of 8 over n squared times the sum from I equals 1 to n of I, plus the limit as n approaches infinity of 2 over n times the sum from I equals 1 to n of 1. Now I have these summation formulas back in my notes. I know the sum from I equals 1 to n of I is n times n plus 1 over 2. And I know the sum from I equals 1 to n of 1 is n. So now you can see these n's are going to cancel. One of these n's are going to cancel, right? And I'll substitute it all. Distribute the 4, distribute the n here. And the limit as n approaches infinity of 4n over 4 plus 4 over n is going to be 4. The limit as n approaches infinity of 2 is going to be 2. And when I add those together, I get 6. So it turns out if you were to solve this definite integral from 0 to 2 of 2x plus 1 dx, you would end up getting 6. I'm going to stop this part of the video for now, and then I will pick up and do some more examples with you in the next video. I just don't want to overwhelm you with too much stuff in one video.